Having redundant switch links in your network is a bit like having extra lanes on a highway. It helps keep traffic flowing smoothly, even if one lane gets blocked. But just like too many lanes without proper traffic signals can lead to chaos, too many network links without control can create loops. These loops are like those never-ending traffic jams that swallow your entire afternoon. They consume all your bandwidth quickly and can bring down the whole network. That's where Spanning Tree Protocol, or STP, comes in. Think of it as the traffic cop, part of the IEEE 802.1d standard, that steps in to prevent unnecessary paths and ensures there's just one active route between any two switches. If an active link fails, STP is on the job, opening up a new lane to keep your network running smoothly. In the world of enterprise switching design, STP is as crucial as traffic lights at a busy intersection. Let's talk about how Spanning Tree Protocol, or STP, selects its leaders. It's like hosting a little election in your network. First, we need to pick the root bridge, which is basically the mayor of your network. This honor goes to the switch with the lowest bridge ID. Now, this bridge ID is a combination of its priority and its MAC address. The default priority is set at 32768, but if there's a tie, the switch with the lower MAC address takes the title. Once we've crowned our root bridge, all of its ports start forwarding traffic, like an express lane for data. Next up, each non-root switch needs to identify its root port, which is sort of like finding the shortest route to City Hall. Each switch chooses the port that provides the lowest cost path to the root bridge. This cost is determined by the port speed, so the faster routes end up costing you less. Finally, on each network segment, we need to select a designated port. This port should have the lowest cost to reach the route, becoming the main avenue for data. Meanwhile, other ports on that segment become blocking ports, like streets closed for construction. This prevents data from endlessly looping around, ensuring everything keeps moving smoothly. Imagine three switches forming a triangle: STU1, SWIP2, and 3. Each is connected by redundant links. Think of SW1 as the big boss here. It's got the lowest bridge ID and gets the root bridge title. Now, 2 and 3 need to play nice. They each choose their root port, which is the one that connects them directly to SW1. But wait, there's a bit of a wild card in the mix. The connection between SB2 and SB3 could potentially cause some chaos by creating a loop. SB2 decides it's going to take charge on that link and becomes the designated port because it's got a lower cost to reach the root. SB3, on the other hand, has to settle down. Its port facing S2 goes into blocking mode, effectively breaking the loop and keeping everything running smoothly. Crisis averted. Spanning Tree Protocol, or STP, relies on 3 main timers that are crucial to understand. First up, we've got the hello timer, set to 2 seconds. Think of it like sending a postcard every couple of seconds saying, "Hey, still here." That's the root bridge's way of keeping tabs with the network. Next, there's the max age timer, set at 20 seconds. This is how long a switch keeps a BPDU around before deciding it's past its expiry date, much like that milk you forgot about in the fridge. Lastly, we have the forward delay timer, clocking in at 15 seconds. This is the period a port spends in the listening and learning states before it can start forwarding packets. Now, when a link goes down, the entire convergence process can take up to 50 seconds. That's 20 seconds for max age, plus 15 seconds each for listening and learning. It's a bit like waiting at a red light that takes forever to change. That's why rapid STP exists. It speeds things up drastically, allowing convergence in less than a second. Picture going from dial-up speeds to fiber optic, much faster and less frustrating. Let's dive into 5 common pitfalls you might encounter with Spanning Tree Protocol. First up is the root bridge election. It's all about the bridge ID, which acts like a ranking system. It checks priority first, and if there's a tie, it looks at the MAC address. Just remember, in this scenario, lower numbers are better, like golf scores. Aim for the lowest. Now, each switch, except for the root switch, has one root port. Think of it as your favorite shortcut to the root bridge. Then you've got the designated port, which is a bit more social. Every network segment gets one designated port. Imagine it as the VIP lane on each road. Here's a gotcha that trips up many. A port can't double dip as both a root port and a designated port. It has to commit to a single role. And then there's Cisco's PVST+, which adds an interesting twist. It runs a separate STP instance for each VLAN. This means each VLAN can have its own root bridge. Great for spreading the load, but your CPU and memory will have to put in a bit more effort. Keep these points in mind, and you'll be steering clear of these common STP snares. That's a wrap on the spanning tree protocol. We walked through root bridge election, identified root ports and designated ports, dug into port states, and had a chat about timers. To really nail this down, swing by Courseiva.com for some CCNA practice questions. Keep going, you're doing fantastic.